Students, welcome to the class 4 fifth class. So in the yesterday's class we have learned regarding the Orgel diagram, and I had given you homework also. So D1 D9 system we did yesterday, so I said you to go for other configurations for Orgel diagram because you have done already this in the previous semester. So one note, you can see that the magnitude of absorption and splitting depends on the nature of the ligands. Okay, now here there is four complexes: titanium hexachloro, hexafluoro, hexaaqua, and hexacyano. So they are showing this absorption 13,000, 18,000, 20,000, 22,000. So how you can arrange this? So it depends on the nature of the ligand. So if you see the electrochemical series or splitting series of the ligand, so cyanide is having the highest splitting energy here, and that's why I can show that this is the greatest absorption, followed by aqua, and then followed by the aqua. Like this I can give it. Okay, so 22,000 will be for the cyano, then 20,000 will be from the aqua, 18,000 will be fluoro, and 13,000 will be from chloro. So because it is the weakest splitting ligand, so this is how the one question from the computer examination. So depending on the nature of ligand, so we can see that the absorption also differs. The order will be like this. So you should know the series of this splitting energy of the ligands. In further classes we will have the series also. Now coming to the one more example I have taken here. So sometimes they ask you, so given complex is there, hexa aqua cobalt plus 3. So 3 transition it is showing. So assign this transition they will ask. So 8,000, 13,000, 18,000. So what you have to do? So hexa aqua cobalt is there in plus 3 state, mean D6 system. Okay. So 1, 2, 3, 4, 5, 6 system. So when you this is there, so on the radiation, so you can see that one of the electron will jump and there is a transition. Now you have to assign these 3 transitions. Yesterday we had taken the original diagram. So which system? D6. So you have to see. Yesterday the blueprint blue, this one you have to see of the diagram. 2 diagrams we had taken for Orgel. So D6 means we come with this type of ground terms. So D6 you see which ground term will come. So I have just taken F and P. So you mention here this term symbol here. So atomic term here. So you will come to know. So we know that D6 will come like this: A2 A2, then T2 T2, T1 T1 F, and T1P will split T1P. So from the yesterday's diagram. Okay, so D6 you see, so you can see the ground term from the previous classes. So for D6 which ground term, that also I will give you to the work, so you can do it, and you can mention here the atomic term symbol here term. So here now 3 transitions. What will be the 3 transitions now? So you can see here, so T1G will be the ground terms from T1G to T2G. Okay, F. So T1G to T2GF. The next is again T1G is ground term to T1GP, second transition, and third transition will be again T1GF ground term to A2G, like this. So these are the 3 transitions, and already has given 3 8,000, 13,000, 18,000. So this will be 8,000, 13,000, and 18,000. But in some cases, because of the high energy from here to here, it requires high energy. Okay, so because of that, you can see here sometimes this transition is not seen. Okay, so only 2 transition is seen from this to T1G to T1 T2GF and T1G to T1GP. So these two, so this requires higher energy, so this transition is not seen sometimes. So it shows only 2 transitions. So you should know this. Okay, so though he has given, but the third transition is requiring more energy, so it will not be sensed by this diagram. Okay, by which we are taking this, computerizing this. So this is what they will ask in the competitive examinations. Okay, so this is how the Orgel diagram. I have taken one of D6 of this diagram, and yesterday's we have shown the doublet D splitting also. So simple D1 D9, and remaining whatever is there you can go for nickel also. So nickel hexa aqua plus 2. Okay, so you can try for this and assign the transition, how many transition it is going to take with respect to this diagram. So very simple. So try it home. So for all D1 to D9, so for all you put Orgel diagram, mention the transitions, whatever is possible, and if you have any doubt you can ask, or you can put some questions, so we'll solve that. Okay, go for the NET questions or something like that, so or any competitive, so you can solve that based on the Orgel diagram, and if you have any doubt you can ask me. Next is TS diagram. Tanabe Sugano, Japanese scientist. He was a Japanese scientist, and he, What is the difference now? So TS diagram is a new thing for you, because in last semester Orgel diagram you had learned. So this semester TS diagram. Why this? See, the difference between this is also a correlation diagram, TS diagram, but it's quantitative. Quantitative means what? You can calculate the energy delta naught value, as well as B. B means what? Raka parameter. So this we could not find here, but in this case energy you can find EB and B parameter, Raka parameter, delta naught value you can calculate. So we'll do it. Then this diagram is applicable for both high spin and low spin. This is the second useful parameter for this TS diagram. So both, but this was only for high spin, but this you can see here, you can for low spin as well as high spin. So weak field and strong field ligands, this is applicable. This is applicable TS diagram. Next, see here. So you can plot this diagram, TS diagram, with respect to E by B versus delta naught by B. So energy by Raka parameter with splitting energy. So I have written here B is nothing but Raka parameter, RACH, Raka parameter, and delta naught is crystal field splitting energy. Okay, so delta naught is crystal field splitting energy. Now see the diagram. Simple it is compared to Orgel diagram. So this TS diagram is represented in this way. See here. So lowest ground term is there, no? So it is made flat. It is made horizontal in this way. Okay, totally flattened here. And the second in Orgel diagram, what we had done. So this is what we had done in the Orgel diagram. So for D1 like this here. So this was T2G and this was EG, something like that yesterday's. Is it right? So T2G, we represented this transition for T1 system like this for the Orgel diagram. So in Tanabe-Sugano diagram, what is done? This is flattened. This is taken in horizontal. Lowest ground term is there. So this is taken as a horizontal this way, and this transition is shown like this. This is the what difference of the TS diagram. This is over. And rest of thing is what? Yes, so here only same spin multiplicity was considered in Orgel diagram. So same triplet, triplet, doublet, doublet, and ground terms. So here in this TS diagram, all ground terms you can see here. So I have taken triplet F, singlet D, triplet P, singlet G, singlet S. See, so all is mixed here. So it depends, the ground term, the spin multiplicity is varying here. So you can see in TS diagram all mixed spin multiplicity could be obtained. The transitions could be shown in this. Is it right? But in Orgel diagram only same spin multiplicity has to be, for example, doublet D, doublet T2G2, doublet TG like this. But in TS diagram it's not like that. So it's a mixture. You can see here correlation diagram. Okay, we'll discuss this. So this is one difference you have to keep in the mind. And the second is what during this what will happen also when we are taking this different terms here. So sometimes what will happen, so there will be some terms which is having the same spaces here. So you can see here singlet EG here is there, singlet EG in this case also is there. So you can see here singlet T2G, some this here case is there. So there are so many terms will be there which having the same spin multiplicity. So then we are drawing the TS diagram. Some of this curves like this, when some of these curves what we are showing here, so they deviate. For example, if one curve has come like this, so next curve if you show it will go like this. Okay, or sometimes it will come like this. So they deviate, curved lines will be got here. So why these curved lines are non-linear lines? So non-linear lines is got here. Why? It's because whenever they are crossing with same spin multiplicity, they reflect, they curve. That's called spin crossover. That term we call it as a spin crossover. Okay, spin crossover means what? Spin crossover means sometimes as we increase the field here. So you can see here, as we increase the field from lower field to higher field, what will happen? There is spin crossover. That means what? Here low, if it is starting from high field, then it will convert to low field. See, that means high spin to low spin. The complex changes from high spin to low spin as we increase the field from here like this. That means the ground term also changes. If it is here a quarter triplet T2G is a ground term here, as I increase the field here, so what will happen? Triplet T2G will convert to doublet T2G. So this system is happening here in TS diagram. That is total ground change term is going to happen from triplet T2G to doublet A2G. So in Orgel we have not found that, but here there is a completely ground change term change will be changing here as the field is increased, and that point we call it as a spin crossover. We call it as a spin crossover like this. Okay, and the curving of the line, so that is non-crossing rule. So one more is coming, that is non-cross rule. Non-cross rule, they will not cross. If the spin multiplicity is same, then they will not cross, and that's called non-cross rule. So these two things in TS diagram is very much technical words is being used. So non-cross rule and spin crossover. So one of the typical correlation diagram I have taken here. So you can see here, as I said, triplet F, you know how it is splitting, triplet T1G, triplet T2G, like this, the singlet D, singlet EG, singlet T2G, triplet P, triplet T1G, singlet G. So you can see singlet EG, singlet T2G, singlet T1G, singlet A. So these are is splitting orbitals depending on the singlet S A1G. Now you can see here triplet P. Now we are learning this system in T2G 2 system, that is 2 electron. So 2 electrons. So initially how it will be filled, T2G2, then it will go, one electron will be excited, T2G1, EG1, and finally both electrons are excited to the EG2, like this. Is it right? Now you calculate the microstates here. T2G2. So factorial we have known T2G. So 6 factorial divided by, because 3 is a triplet, so 6 factorial divided 2 electron means what, 2 factorial into 6 minus 2 factorial. If you calculate this, I think you get 15 microstates. Here you get 24 microstates. Okay, you calculate this for T1G, EG1, and here you get around I think EG2 is there, so 6 microstates. Just calculate it here with the factorial term here. Now you see here, so 15 microstates is there, so you can see here. So it will split into triplet T1G. So that's 3 3s are 9, so triplet means 3 3 3s are 9, 10 11 12 13 14 and 1 15. See here, 15 microstates splitting into 15. Similarly 24 microstates, so for this is 3 3s are 9, 10 11 12, 3 3 9, 18 19 20 21 22 23 24. See, 24 microstates I have made it here. Similarly here 6 microstates, so 2 3 4 5 and 1 6, like this. Is it right? So this is how the microstates we can make. And now see correlation, now you have to correlate it in here. So triplet T1G will be the ground term here, also triplet T1G, this is correlated. So triplet T2G is here, triplet T2G, so this you have to correlate. Then triplet A2G is triplet A2G, so here it goes like this. This is called correlation. Every whatever ground terms is there, so same ground term will be here, and you have to correlate now. So this is now, so singlet E1G, singlet E1G, like this. Then here triplet T1G, triplet T1G. Then singlet A1G, singlet A1G, somewhere it comes. Then here triplet we have done it here. Then finally here singlet S, singlet S, here singlet S. So like this you go on correlating, and this becomes a correlating diagram. So like this correlation diagram in TS, very very complicated, like this. See, so in simple case we have gone this case for what D2 system. So you can see that for D2 only so complicated. So you can think of what D3, D4, D5. It's very very complicated, but we can do it in textbooks and all. The simple way they have given for D5 everything. And here the transition takes place now. So this is a ground term, and here the transition will take place like this. Okay, but here one case is one case here is what the transition is taking place with different multiplicity, that means low spin as well as high spin. But in Orgel diagram, so only one spin multiplicity, the transition was there. So this is how the large difference we can see between the TS diagram, between this TS diagram as well as Orgel diagram. In the next class we will learn regarding the TS diagram and how we can calculate the delta naught value and Raka parameter. What does this mean? In the next class. Hope you understood this. If any doubts is there, you can ask. Thank you.